Okay, review here of chapter 4. We'll start with our basic definition of probability. Probability of an event occurring is our number of favorable outcomes over our number of total possible outcomes. Key here being is our probability is always over the number of total ways that something can happen. So if I want to find the probability, if I roll a single die, okay, a single die has 6 faces, a 1, a 2, a 3, a 4, a 5, or a 6. So my probability is going to be over a total of those 6 possible combinations. Now if I wanted to find the probability of rolling a 3, in my listing here, there is only 1 3, so my probability of rolling a 3 is 1 out of 6. Couple of side notes here. Number 1, this listing right here of all my possible outcomes is referred to as a sample space. So a sample space is a listing of all possible outcomes of our probability experiment. Along with that, our probability can be written as a fraction, like I have up above with a 1/6. It can be written as a decimal. If you were to take out your calculator and take 1 divided by 6, we get a decimal like 0.1666 repeating, so I'll just go 4 decimal places and say 1.1667. Or our probability can be written as a percentage. And that percentage, we'll just round, we'll go 16.67%. Okay, so our probability can be written any one of those 3 ways. Not there's a one way better than another, but a lot of our work is centered around the fraction, so we've written a lot of our answers as fraction, and a handful of those as decimals. But again, any one of those 3 is acceptable. It can be any one of those 3 forms. Our probability should always fall between 0 and 1. If our event cannot occur, then the probability is 0. Can't spell, so let's try that again. Probability cannot occur, the probability is 0. So, quick example, I guess. Probability of a tsunami in the state of Iowa today is 0. That's not going to happen. You don't have tsunamis in Iowa, so that cannot occur. If an event is certain to occur, then the probability is 1. So the probability that, what can we say here? Probability that the sun goes down tonight, sun sets, the probability is 1. That's certain to occur. That's going to happen regardless of what else happens in the world. With that being said, anything else is going to fall between 0 and 1. So our probabilities always fall between 0 and 1. They can't have values of 1.2 or negative 0.6. They must occur between 0 and 1. As we start talking more about that sample space I just mentioned above, sample space, again, lists all of our possible outcomes of an experiment. Okay? All outcomes of a probability experiment. One thing we had in our notes was we did a tree diagram. That tree diagram can help us list our sample space and ultimately find our probabilities. So let's say we're going to flip a coin 3 times. The first time I flip that coin, it can be either a heads or a tails. The second time I flip that coin, in either instance, it could be a heads or it could be a tails. And our third coin also has those same 2 options in each instance, so I keep my branches going out here to where I have flipped my first coin, my second coin, and my third coin. And if I follow my branches out, it lists my sample space for what could happen when I flip a coin 3 times. Tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So you can see 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different things that can happen. Those 8 things are the sample space. So again, these 8 combinations, so to speak, are the members of our sample space. So if we wanted to find the probability that all 3 were heads, we would count that up. That happens once out of 8 times. So our probability is 1/8. If we want to find the probability of 2 heads and 1 tails, we have 1, 2, 3, 3 of those, so our probability is 3/8, and so on. So our tree diagram can help us draw or come up with our sample space and also ultimately find our probability. Another example in our book, we have the rolling of 2 die. So if I did die number 1 here, we can get a 1, a 2, a 3, a 4, a 5, or a 6. If I go down here and do die number 2, I can get a 1, a 2, a 3, a 4, a 5, or a 6. So then, if we were to look at ordered pairs here, I can get a 1 and a 1, a 1 and a 2, a 1 and a 3, 1 and a 4, 1 and a 5, 1 and a 6, and so on. So I'll just take a quick second to fill this out. Listing again all of our combinations: 3, 3, 3, 4, 3, 5, 3, 6. Probably be a little bit easier if my pencil worked on this screen better, but we'll make do. So as we go through here and write down each of these ordered pairs, those ordered pairs make up our sample space. Now the one in the book's probably easier to read, but I hope we get the general idea. So you can look in here, we have 36 different things that can happen. 36 different ordered pairs. Again, the order matters, so it does make different ordered pairs. A 2 and a 1 is not the same thing as 1 and a 2. We're talking about 2 different die. So we have 36 total possibilities. That's our sample space. And then we can figure our probability out of that based on what we want to find. We want to find probability of rolling a sum of 5. You can see 5 is 1 and 4, 2 and 3, 3 and 2, and 4 and 1. So there are 4 of those, and we've established probability should always be in simplest form. So our probability is actually 1/9. Our fraction of 4/36 is simplified down to be 1/9. Okay, so there's a look at sample space and drawing those. Sample space is the basis for a lot of probability. From here, I think we had our addition rules. So our addition rules were based on one basic premise, and that's whether or not 2 events were mutually exclusive. If they are mutually exclusive, they cannot occur at the same time. In addition to that, with our addition rules, there's 2 of those. We'll touch on that in a minute. But our addition rules revolve around the idea of selecting just a single item, the probability of a single item. So in other words, I might be drawing a single card out of a deck of cards. I might be selecting a single person for a certain task, something along those lines, but we're selecting a single item. So 2 events that are mutually exclusive cannot occur at the same time, and our addition rules apply to selecting a single item. So we'll go back to our mutually exclusive idea. 2 events that are mutually exclusive, let's think about a deck of cards. If I want to find the probability of pulling out a single card and I want that card to be a jack or an ace. Okay, those 2 events are mutually exclusive because they cannot occur at the same time. And to find our probability, we simply add those two individual probabilities together. So there's 4 jacks in a deck of cards out of 52. There's 4 aces in a deck of cards out of 52. So our probability is 8 out of 52, or that simplifies to be 2/13. If two events, so I guess as a rule, the probability of A or B, this is our addition rule number 1, is equal to the probability of A plus the probability of B. Should be pretty straightforward. We add those two events together, and that gives us our probability. Addition rule number 2 revolves around the idea of addition rule number 2 says pretty much the same thing, but these two events are not mutually exclusive, which means they can occur at the same time. So it's the probability of A minus, or plus the probability of B minus the probability that both can occur. So addition rule number 2 would be an example. Let's say that our deck of cards, this time we want to find the probability of an ace or a heart. So if you think about your deck of cards, there is a card that is an ace of hearts. So this is an event where the two events are not mutually exclusive. So we would add the probability of an ace, which is 4 out of 52, to the probability of a heart, which is 13 out of 52. But we have that one card that is an ace of hearts, so we'd add that single card in twice. We don't want to add one card in 2 different occasions, so we subtract out that one ace of hearts, which gives us 16 out of 52, or 4/13. So there's a basic quick look at our addition rules. Addition rule number 1 is 2 events are mutually exclusive, and addition rule number 2, where 2 events are not mutually exclusive. Bottom line is addition rules apply to the idea or the concept of selecting one item, whether it's one card, one person, one whatever. It's one item as opposed to multiple items, because our multiplication rules apply to selecting more than one item. So we might select several items in succession. So we might take 3 cards out of a deck of cards. We might select 5 people at random, several items in succession. So again, 2 or 3 cards out of a deck of cards, 5 people from a class, whatever, to find a certain probability. And the multiplication rules are based on whether 2 events are independent or dependent. If 2 events are independent, the outcome of one does not, I repeat, does not affect the outcome of another. Event. Okay, so independent events, the outcome of one has no bearing on what happens with the next one. Dependent events, the outcome of an event depends on what happened with a previous event. So hopefully, or I think the easiest way to illustrate that, if I'm going to draw 2 cards out of a deck, and I want to find the probability of an ace and then another ace. Okay, we start out with if after each draw the cards are replaced, then we have independent events because of probably the first card being an ace is 4 out of 52. Once we pull out an ace, we put that card back in. We still have 4 aces. We still have 52 total cards, so our probability is 4 out of 52 times 4 out of 52. If the cards are not replaced, so now they are not replaced, now they become dependent events. So it's still the same example, probably with 2 aces. The first probability of an ace is still 4 out of 52, but now to move on to the second event, that first card had to be an ace. So there are only, and we haven't replaced it, so we pulled out 1 ace. There are 3 aces left, 52 total cards. So our probability, oops, not 52 total cards, 51 total cards. Okay, 1 less ace, 1 less total card. So 4 out of 52 times 3 out of 51. So those are our 2 scenarios, dependent versus independent. Our rule up here, the probability of A and B is simply the probability of A times the probability of B. Probabilities don't change from one event to the next. They're independent of each other. And here, for addition or multiplication rule number 2, probability of A and B is the probability of A times the probability of B, but we can't do B unless A has occurred. So this last slash mark is read probability of B assuming that A has occurred. And those would be our 2 multiplication rules. With our multiplication rules, now I just did for 2 cards, we could do this for 3 cards, 4 cards, 5 cards, whatever. It's multiple events happening, not just 2. It can be 3 or 4 or 5 or any number past that, I suppose. But we have a couple of scenarios that pop up. If we have basically a problem that has a lot of information that needs to be sorted out, that tree diagram can help. So if you recall, out of our note packet we had, I can't remember, it was John maybe that was going to drive his car or take the bus, depending on whether it rained or not. So we draw out that tree diagram to show what happens, and that just sorts things out for us, and we can follow our branches out to find those probabilities. And then we also have a special rule with multiplication rules. That's find the probability of at least one event happening. When we do the probability of at least one, a shortcut version is to simply take 1 minus the probability, and we've labeled this as the opposite. So the opposite of at least 1 is none. And that ties back to the idea of a complement event. If I'm going to pull 5 cards out of a deck of cards, and I want to find the probability of at least 1 heart, if I went the long route, I'd have to find the probability of 1 heart, of 2 hearts, of 3 hearts, of 4 hearts, and of 5 hearts for each of our 5 cards. Now, a shortcut version would be 1 minus the probability of 0 hearts. That's a 1-step, maybe a 2-step, find probably 0 and subtract it from 1, as opposed to finding probability on 5 different occasions and adding those 5 together. So we run through several problems with our at least one event occurring. Shortcut, 1 minus the probability of, and in this case we've written none, but we've also used the term opposite. So the opposite of at least 1 is 0. So reword that. It might help to write it out in this format and then do the actual work itself. As just like up here with our addition and multiplication rules, it might be beneficial to write out the actual information from the problem, then make the substitutions with the probabilities that are labeled in the problem. And then we ended chapter 4 with what we have labeled as our counting rules. So our counting rules would consist of the fundamental counting principle. Sure wish this pen would work better. Fundamental counting principle. And the fundamental counting principle simply says if we're selecting one item out of multiple, one item each, maybe I should say, so let's go back. One item each out of several categories. We want to know how many ways that's possible. We simply multiply the totals together. So a quick example, let's say we're going to go to a restaurant and we have a choice of 3 appetizers. We have 4 main entrees, and we have 5 desserts to choose from. So the different ways to put those meals together is simply 3 times 4 times 5, or there are 60 different ways we can have our meal with 3 appetizers, 4 entrees, and 4 desserts. Fundamental counting principles should be pretty straightforward. We had a factorial function. That factorial, such as 6 factorial, simply means to multiply each number below that initial number until we get down to 1. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. We get, what do we get here? 624, 120, and 720. So we get 720 as a factorial. Those factorials were used in our permutations and combinations. So a permutation is an arrangement of objects and an arrangement of objects where the order that we arrange those in does matter. So order matters. Okay, so when I say order matters, the example I threw out in class was if I were to give $50 for the first person done with their homework, $25 to the second person done with their homework, and $10 done to the third person done with their homework, the order you finish in matters because you'd rather finish first and get $50 as opposed to finish third and get $10. So the order matters, so that makes it a permutation. Now we shortcut this with our calculator. On our calculator underneath the math function and then the probability is a button or a function that says NPR, where N is our total number and R is the number that we're choosing. So let's say our class has 30 students. We have 30 people to choose from. I'm going to award 3 places, so it's 30P3, and we type that into our calculator to get our permutations or the number of ways that that would be possible. From there, our other arrangement or counting rule is called a combination. Combination is also an arrangement of objects. But here, order does not matter. And just to go off of my same example, let's say I'm still going to give prizes for the first 3 people done, but $10 is for first place, $10 is for second place, and $10 is for third place. Now, whether you finish first or third, you still get the same $10, so the order you finish in doesn't make a difference, so that makes it a combination. And again, a shortcut version on our calculator, we have an NCR button, or in this case, we'd have 30 people in our class, C and 3, and so we have 30C3, a combination because order did not matter. And then we applied those counting rules to some of our probability. So kind of backtracking here, the wording on these is going to say how many. And then we progress on to finding probabilities. if we find probabilities using these counting rules, okay, probability is a fraction. So in most of our examples, we started with a fraction bar, found our total number here in the denominator first, total number of ways it can happen, and then met our criteria for what we want to have happen here in the top. So let's say, just as a quick example here, we're going to select, out of 30 students, we're going to select 5, and we want to find the probability that 3 made A's on the on the chapter 3 test. So actual numbers, we would say, let's say that 12 overall made A's, which means 18 made A's. 18 made a grade lower than an A. Okay, so with our, we're going to find, I'm getting kind of stuck here, find the probability, I wrote that down already, my bad. Didn't realize what I written down. So we'll find the probability that 3 made A's on the first test. So overall, we have 30 students in our class. We're going to select 5 of those. The order we select those in doesn't make a difference, so we're going to select 5 out of our class of 30. Out of our 30, 12 made A's, which means 18 did not, and we want to find the probability that 3, so 12 or 12, 3 made A's. Since we're selecting 5 total people, that means 2 of the people we choose did not make A's, and there's our probability. And once again, our probability can be written as a fraction or as a decimal. With our calculator version, this would probably be a decimal, but again, a fraction would suffice. But 12C3 times 18C2 over 30C5. We made this point, but I'll make it again. Notice that our 2 categories of A's and not A's add to be our 30, and our categories of selecting A's and selecting others equals our total number being selected here. So there's our counting rules and probability. And that is a quick review of Chapter 4.